Hydrogen is more than drinking water. Without it, there is no food, no plastics, no industry. A moon settlement can run short of almost anything else and improvise, but it cannot run short of hydrogen. And the moon is stingy with it. Ben will tell you the polar deposits are a bunch of question marks followed by question marks. I say it's a pretty big lake. So, hydrogen.
Hydrogen, right. Hydrogen's first because it's the most common. It's probably the most important element that we're going to need for a lunar settlement. So let me bring my thing up. So I've broken this down into three things. So uses, right? The primary use for hydrogen is going to be for water, right?
Yep.
Earth life is water-based. You don't have water, you don't have life. And a settlement's going to need a lot of water for a lot of reasons. It's going to need it for agriculture. It's going to need it for industry. It's going to need it for life support. It's going to need it for fun. It's going to need it for maybe radiation shielding. Who knows?
Yep.
So water is the main use for hydrogen, but we have other uses as well. Mentioned agriculture. You know, you can use
hydrogen.
Fertilizer, hydrocarbon fertilizer. It's kind of, I think there's better ways to make fertilizer, but we can get into that later. But there are other agricultural uses for variations of hydrogen besides water. Rocket fuel. Now you can use liquid hydrogen, liquid oxygen rockets, which I think is a criminal use of limited lunar hydrogen, but people are planning on it.
I agree. You should not use lunar hydrogen for rockets.
Yeah. I think future generations of lunar settlers will be very angry about that, but we're not in charge, so we'll see what happens. And then industrial processes. The one that I think of is hydrogen reduction of iron oxides in basalt. You run the hydrogen, you heat up the basalt powder, you run hydrogen through it, and it strips the oxygen off, forming water vapor and leaving iron behind. So that's one way. There's other hydrogen processes that you can use.
And industrial processes as such are not as bad, well, are much better than rocket fuel, because rockets, they are not inside, while industrial processes will be inside. So everything that are output from an industrial process will effectively be recycled. So it doesn't really matter if you do the recycling right that you use hydrogen.
Right, yeah. So like for the hydrogen reduction, you get water vapor, you capture it, you split it, you got your hydrogen back, right? I mean, there's losses in all systems, so you'll have to replenish it over time. But if you build it right, the losses will be minimal, and you can just keep reusing that hydrogen over and over and over again. There's no real loss, unlike a rocket, which just blows it right out the back.
Yep.
And then energy storage, right? You can fuel cells, which basically takes hydrogen and oxygen, combines them, produces electricity and water, and then you just go around and break the water up again, or some kind of combustion. So that's what I got for uses for hydrogen mainly. Got anything else you could add to that?
Let's see if I have something. Yeah, iron reduction, we said that's instead of carbon, essentially.
Well, and there are carbon reduction processes too, but the hydrogen reduction requires the least amount of heat and energy input. You start getting into the carbon reductions and it requires more energy.
Yeah, and carbon is not more plentiful than hydrogen, so that doesn't really help. So hydrogen reduction is fine, and there are companies working on that. A couple quite nearby here, actually, north of Sweden. So that's mining and mineral production, factory. We mentioned nitrogen is about half the nitrogen on Earth is produced by Haber-Bosch process, which essentially strips nitrogen out of the atmosphere. That doesn't really work on the moon because unless we first put nitrogen in the atmosphere, it's not a way of extracting nitrogen. It's just a way of getting it back from the atmosphere in case we don't use beans or some plants that do that.
Right. Well, yeah. Well, nitrogen.
Refining, hydrocracking, desulfurization, methanol production, float glass. Hydrogen is often used as oxygen-free atmosphere to keep glass from oxidizing.
Oh, okay.
Semiconductor, same thing there. Carrier gas for reactive precursor and annealing atmosphere for wafers. Welding and cutting, oxyhydrogen flame, pretty common for both welding and cutting.
Yep.
Yeah. Water is used a lot for different things. Standard chemical engineering, there's a lot. And in the greenhouse, of course, ammonia, and water in the greenhouse. Yeah, that's sort of it. Habitat, of course, we wash ourselves in water, we drink water.
Yeah, I consider that all part of the life support system, keeping humans happy and alive.
Yeah. Yes, that's that's a vital use of hydrogen in the meaning of the word. So no, I think you covered most of it. I just went through my list to check.
Okay, and then the next section I had was, and I think we could use this for all elements, but for hydrogen, the next one is substitutes. And I had, there really is not much of a substitute. When you need water, and it's hydrogen and oxygen, and you can maybe find substitutes, but if you need water, that's pretty much what you're stuck with. And if you need hydrogen for another process,
well, to use it as a reactive agent, you can replace it. I mean, steel has been made with carbon more than it has been with hydrogen, so there is a substitute. As we said, it's not really a good substitute because it's the same problem.
I've never heard of hydrogen replacing carbon and steel, right? But I mean, I guess you could maybe. I don't know.
In steel refinement, yes, it's being done.
Oh, okay.
There are, and Sweden is apparently pretty forward on that, making carbon-less steel. That's environmentally friendly because you don't want to use carbon because it ends up in the atmosphere, while hydrogen that becomes water and isn't as harmful in the atmosphere.
I have to look into that, the material properties of this type of steel. But yeah, you can for certain processes you can definitely sub out, or you just use a different process, and it may be less optimal, but there are solutions. But there are no substitutions for water for life support or for agriculture and stuff like that. So
drinking water and watering plants, there is no other thing than water that will work there. You can dilute the water somewhat, but that's a different story. Not hydrogen.
Right. So hydrogen is critical, right? We're not going to get away from not having a lot of hydrogen. And then the third thing is solutions, right? And so I basically brought it down into two categories. And the first one is find it locally, right? So the first one is we can mine it, right? And so the regolith, the layer of fine rocky material on the surface, has been implanted with hydrogen over millennia from the solar wind. And so here's some numbers. So the Apollo samples that came back ranged from 3.2 to 60.2 micrograms per gram, or about 3 to 60 parts per million, with an average concentration of 36.3 micrograms per gram, or 36.3 parts per million. So there are some interesting things about that. One, that's not a lot, right? 36 parts per million is not a lot. It is very low concentration. But they did find out that the hydrogen concentration remained the same throughout the depth of the sample, right? So it wasn't concentrated on the top and less on the bottom. It's pretty much the same throughout. And they think that's because over time, impact gardening buried top levels and exposed new levels that then got implanted with more hydrogen. So we don't just have to scrape off the top 3 centimeters and that's all we're get, right? We could go down into the regolith to find hydrogen if we have to. And they also found that the concentrations increased with regolith maturity, right? So that makes sense. The longer the regolith has been exposed to the solar wind, the more hydrogen is managed to capture. So highland sites will probably have higher concentrations than the mare because they're just older.
And then they have also deeper regolith as well, right? And you're saying it's regolith that has the hydrogen. The rock itself doesn't. It has to be fine powder then.
It's the regolith because I didn't see the mechanism in there, but I believe I read that it's adsorption. So the hydrogen is sticking to the fine particles. It's not chemically bound.
Yeah, it's sticking to a surface, and the fine particles has more surface. Yeah.
Yes. So the regolith, the finer the particles, probably the higher concentration. I didn't see that, so don't quote me on it, but like a solid chunk of basalt is not going to have any extra hydrogen from the solar wind. It's fine particles, the hydrogen's absorbed to the surface. So if we use
except the glass beads.
What's that?
So except the glass beads, but that's
a
different source. Yep.
You're jumping ahead. We'll get to the glass beads.
I like those.
Yeah.
But continue.
Right. So anyway, I just want to say, so if we used the average concentration of 36 micrograms per gram, a ton of regolith would produce 369 liters of hydrogen gas at STP, right? Standard temperature and pressure. Which sounds like a lot, but according to the internet, you need 1,244 liters of hydrogen gas to produce a liter of water at STP. So at that, using that number, we would have to move 3.4 metric tons of regolith to produce a liter of water, based only on hydrogen production and not oxygen. 3.4 metric tons of regolith is an awful lot of regolith to get a liter of water. So yeah, it's not something you're going to do as a primary source. And remote sensing
then you need to really recycle hard. Yes.
And remote sensing has shown values up to 150 parts per million, which is not a huge jump, right? But even at that concentration, you're still moving a ton of regolith to get a liter of water, which is still a lot. They also showed that higher concentrations can be found at higher latitudes. So the Apollo samples were basically equatorial, right? So it's thought that the higher in latitude you go, the lower your day span temperatures, which results in less energetic volatilization of the hydrogen during day span, which results in less loss to space. And that's why, the hydrogen kind of moves during every day span cycle. And it probably moves to the poles just because as it moves towards the poles, it has less energetic every day that it volatilizes.
Yeah. And also when it reaches the pole, well, essentially what happens to hydrogen on the surface or any volatiles on the surface is that sun goes up and it vaporizes, and then it drifts around until the sun goes down, and then it freezes and falls down, and then that keeps happening until it reaches the poles. When the sun goes down there, it falls down, and then it stays down because the sun never rises.
Yeah, well, that's the next section is the PSRs. Right. So, and then the last thing for this is the glass.
It's sort of the same mechanism close to the poles. Okay, the sun rises, but it's shorter and colder.
Right, and it's all about how energetic the volatilization is. Right at the equator, those hydrogen molecules get very energetic, and some of them just get lost to space. But the less energy they get, then they're not basically they're not jumping as high. or as fast. So you get to the poles and they're not moving very fast.
I would argue against that, actually. I think when the sun ray hits something, then that photon will have the same energy regardless of where it hits, because it hasn't been there is no atmosphere to retard it, break it up.
I don't think it's a matter of.
But what happens on the pole is that the inclination angle is low, so there's much fewer photons hitting, which means that there are less hydrogen. It is not less energetic. It's just fewer atoms that are actually being hit by a photon.
Hey, I'm just quoting what the source said, right? It just said that the thought is that lower day span temperatures result in less energetic volatilization. And then the glass beads that you mentioned. Hollow samples have shown some of the glass beads to have up to 1,410 parts per million of water enclosed in them. So theoretically, you could harvest glass beads and break them up, melt them down, do something to release the water. Don't know how difficult that would be. But we haven't seen like large beds of these things. So I don't know if that would even be a viable thing to look for, right?
Yeah, I think it is like the solar wind embedded atoms as well, that you wouldn't process rock in order to get at those atoms, but you would make sure you salvage them when you're processing the regolith anyway for other purposes.
Right, and that was my last point for this, was that, you know, any process, if you're processing regolith or volcanic glass beads or whatever, you're probably not going for the volatiles as a primary resource, but you'll probably want to make sure you have a mechanism to capture the volatiles that are released anyway. It's just a bonus.
Yes.
You wouldn't want to waste them. So that moves on to the next place, which would be the permanently shadowed regions, right? The PSRs. And everybody's excited about them because we think that there's water in enough quantity of some sort there to warrant extracting it. But Nicholas is sick of me saying this, but I'm going to say it again. The PSRs are a bunch of question marks followed by more question marks, right? They're all basically unknowns, right? We don't know the composition, physical or chemical, of the hydrogen that's in there. They're extremely cold. We have very little experience dealing with those temperatures, let alone operating an extraction process in them. They're by definition very dark. And we just have no idea of the quantity of volatiles inside a particular PSR, right? There's lots of numbers floating around. They're basically guesses, you know, take your pick. And all of our data is from remote sensing, which is great, but you know, it's really all just kind of hand waving until you get in there and actually get some physical samples to back it up. So my point is that PSRs are great. We should definitely get in there. We should definitely do what we can, but it's going to take a while, right? We got a lot of learning and a lot of science and a lot of engineering to do before we can regularly and reliably extract whatever's in there.
Yeah, I do agree on that in spirit. I'm more positive to the numbers that people have been calculating. I'll take that as a best guess rather, and it is a pretty big lake full of hydrogen, or they tend to talk about it as water, and to me it doesn't really matter if it's water or hydrogen. There's plenty of oxygen, and if you have oxygen and hydrogen, and then boom, you have water. That's not a problem.
Well, I think if it's actual ice, it might be a little easier than if it's some complex hydrocarbon that you then got to figure out how you're going to break down.
On the other hand, if it is a complex hydrocarbon, then you get carbon as well, which is about as little of us.
Right.
ice, and probably, I would say.
Yeah, no, I mean, the PSRs are definitely an interesting resource, and we should definitely explore them and learn how to use them and stuff, but we really don't know, right? I mean, it's all remote sensing, right? So we can say, yeah, this is a big PSR, but we don't know how deep it goes, right? It could just be the first 6 centimeters that have enough hydrogen. We just don't know. So
it could be.
it could be.
It could also be, though, that there are sheets of hydrogen a bit down as well. We haven't done very good sensing deep in the lunar soil,
So yeah, I mean,
and temperatures are. I have read somewhere that it's about -20 if you go down a few meters, and then if you go further down, it increases. But if you go down a little bit, then it's quite cold, even by the equator, and colder closer to the poles, obviously.
well, yeah, and you know, if those craters have been around for a very long time up in the PSRs, who knows how much volatiles they've managed to contain? Because they're constantly cold all the time. So there could be layers of volatiles mixed up in the regolith in those craters. We just don't know. There's just everything is an unknown at this point. We need to get some robots in there and start getting some samples and stuff like that.
Yeah.
And then
there's also another source of possible source of hydrogen, and that's carbonaceous chondrites, meteorites, impacting with frozen volatiles.
Right.
That is a bit of a stretch, but it is a plausible one. Nobody has ever found that. So your argument that we have no ground truth is very strong in this case, but it is likely that carbonaceous chondrites have hit the moon in quite large quantities. It is likely that most of those have evaporated on impact, and that has mainly been lost as evaporation and lost into space eventually, or got back down into a permanently shadowed crater somewhere. But there are also calculations saying that if a meteorite has hit with a low enough speed and shallow enough angle, it may have embedded itself as a kind of coolish depth, and those contain compounds that may include both hydrogen and other volatiles. So that there may be volatile mining possibilities here and there on the moon, actually.
Yeah, jumping ahead, but I did pull up an information that carbonaceous asteroids contain up to 10% water with an average of 7%, right?
Yeah.
So yeah, if one of those asteroids hit at exactly the right speed and angle and managed to bury the core of itself under the regolith, then it'd be protected from the thermal extremes, and there could be big chunks of ice under the regolith. Maybe, probably, who knows? Theoretically, it's possible, who knows? Hunting for those would probably be an interesting challenge. Not saying couldn't be done. Probably should be done, because, you know, it's not just the carbonaceous, you know, you find the remnants of a big, you know, iron nickel one, and that's a good chunk of metal that you could just get out of the ground without having to do a lot of processing. So yeah, I think, you know, crater hunting could be a profitable pastime or business model in some case. But it's all very cool stuff, and it's definitely stuff that should be done. Just not sure that's something you want to stake the livelihood of your settlement on until you've done a lot of prospecting, right?
We need to do we need to do a lot of prospecting while we are sending people to the moon, so that at least the second bunch of settlers can live somewhere with resources.
That would be ideal. my concern is I don't want to slow things down just to do the prospecting. So let's get some settlements built while we're doing some prospecting, and then they can do some prospecting and they can sell that data, and the next wave can have better choices.
Yep. Put the first one at a good guess, and then put the next one at a better guess, because the first one found out that that wasn't what we thought.
Right.
It's more of this and less of that. So we still need to import ABC.
Right. And okay, so for finding things locally, the last thing out of my list was lava tubes, right?
Mm.
So theoretically, volatiles could be trapped inside lava tubes the same way as PSRs, right? They bounce around on the surface during the day, they get cold, they settle down, eventually they get trapped way in the back of the lava tube where it just never gets sunlight. And then you get some kind of volatile storage. Again, it's a whole bunch of question marks, right? We haven't physically explored a lava tube on the moon. Still haven't conclusively proven that they exist. We've seen all kinds of photographic and surface scanning that suggests that they're there, but again, nothing's been ground truthed. And the conditions inside a lava tube will be different than a PSR, right? You know, they're underground, they're not exposed to a dark sky. They may stabilize at a higher temperature. Who knows? I mean, it's there. Maybe it contains volatiles. I don't know if that would be a big source of volatiles. A lot of question marks, but it's possibility, right?
Yeah. I would say a lava tube will stabilize to the same temperature as solid rock would have. So it's no different there. Or solid rock, because you can't have a lava tube in regolith. It needs to be solid rock for there to be a lava tube.
Yeah, it'll be basalt, right? Because it's made out of.
Yes, exactly.
So. And then the other section is, if we can't find enough on the moon, we need to bring them in, right? And I'll save the easiest for last. So people have talked about going to near Earth asteroids. Like I mentioned, there's some of them can have up to 10% water. Yeah, that's great. Let's do that. But we also have a lot of technology we have to figure out to make that happen, right? It's not just launch a rocket, get the stuff, come back. So there's going to be time, money, effort to get to where we can actually mine them. And then people have mentioned, well, we'll get them from Phobos and Deimos, right? The two moons of Mars, which is fine. It's the same kind of technology, only now they're even further away and more energy intensive to get to. So
and less sunlight for getting energy there.
Less sunlight and everything. So it just makes it more difficult. And then people say, oh, well, we'll go to the main asteroid belt. And of course, great, same kind of technology, only now it's even further. And, you know, Delta V is even worse. And like you said, you're not even got less sunlight. So you're definitely running on nuclear plants at that point. So importing from space is definitely a long-term goal and option, but it isn't anything that's going to happen anytime soon, right? So the easiest is just to ship it from Earth. You have a shipment of ammonia or methane, you deliver tons of pure hydrogen plus nitrogen or carbon. The moon isn't self-sufficient at that point, it still needs Earth, but you get a simple, fast, easy, known quantity of whatever material you need.
No, I'm saying that we should strive for self-sufficiency. That doesn't mean I think we should send people to the moon and tell them be self-sufficient now. Right. We need to make sure they have a working thought.
Right, and you know, and it's not an all or nothing thing, right? You know, you start off by shipping everything from the Earth, and then once your settlement is at some point where you're like, okay, we're done, it's built. Then you're just replacing losses. And if you build it right, those are going to be a lot less. So maybe you just need much less frequent shipments, or maybe by then you can buy your volatiles from the settlement up at the poles that's mining a PSR for a lot less. So, you know, maybe new settlements need massive amounts to get built, and then they can rely on local sources to keep topped up.
We agree on that.
Right. And that's all I got for hydrogen at this point. I think we need it. Yes. We can find it on the moon. We can ship it to the moon. It's not a roadblock.
There is hydrogen on the moon. In order to get it extracted on the moon in reasonable quantities, we have a lot of prospecting to do to find out not just where, but also how to extract it, because the moon is not Earth, and a moon mine will not be the same as a mine on Earth.
Nope, nowhere close. Totally different environmental conditions, and yeah. So yeah, you're right. A lot of prospecting
and mining totally different minerals as well. Much of what we will, at least initially, mine on the moon will be things that we wouldn't bother with on Earth, because it's way too little of anything in it.
Oh yeah, like I'm interested in extracting the basalt out of the mare, right? Because woohoo, it's got maybe 10% iron. Yeah, nobody on Earth would touch that. That is such low grade, it's not even worth it. So, but on the moon, that's as good as you're going to get for now, and maybe some settlement will get lucky and it'll find the remnants of an impactor, and it'll have tons of iron nickel.
Pure iron nickel.
Yeah.
That's
Maybe
mother lode, I think. Yep.
Exactly. But the problem is that the moon was formed differently than the Earth. The moon has different geological functions, and a lot of functions that operate on the Earth create veins and concentrate minerals that just don't happen on the moon. So we're not expecting to find anything resembling large veins of minerals. It's just not how the moon was developed.
Yeah, but not in most, at least not in most of the ore-bearing veins that we have on Earth.
Yeah, I mean, I'm not saying it's impossible. There's all kinds of anomalies. So, settlement could get lucky and find a huge copper vein, and okay, run with it. But most likely not. All kinds of possibilities exist, but when we're talking about designing settlement technology, we got to design for what we know now, right? Which is very low grade mineral resources and a very limited suite of mineral resources. We can't go on saying, well, we'll design it because maybe we'll find a big load of copper, or maybe we'll find a nickel iron impactor. We got to get, we know regolith, we know basalt, and we know anorthosite. Those are the three main rock types.
I do think, I agree we should design for that. I do not agree we should not design for finding a nickel iron meteorite. That should be pretty easy to find. They are heavy, they are magnetic, and they aren't completely trivial to mine either. Take a big chunk of iron nickel and try to make it useful. That's not. But it's a nice problem to have, but it's not completely trivial that either. And the same thing with the carbonaceous chondrites. We should think about how to extract volatiles from that in a form where it could have survived on the moon. And how would it have impacted the moon, and where to look? It's also things we should think about.
Yeah, I mean, yes, we should, but there's limited resources, there's limited time, and I would rather come up with the Mark I widget to deal with the stuff that we know than to use resources to come up with a widget that may deal with something that we may find. So, given unlimited resources and time, sure, we should go down every avenue, but
plenty of people not doing anything useful on Earth, they could be doing that.
Yeah, but that's not how it's going to work, is it? You're not going to get them working on that. So yeah, and again, if some settlement finds something, there are plenty of people on Earth. Well, not plenty, but there are some people on Earth that would be like, oh, hey, let's figure this out now that you've found, the mother lode.
I think that would be would get some people going, yes.
But let's get some people on the moon first, using the knowledge, what we know now.
That is a good idea. Let's get some people on the moon.
Yeah. Now. Let's do it now.
Yeah.
All right. I think that's a good way to wrap it up. Hydrogen, important.
Yeah. People on the moon, more important.
True.
We'll pack some sandwiches and they can extract hydrogen from that.
Exactly.
That was the argument, and you will notice it is still open. The thing Ben and I kept circling without ever landing on is the PSRs, the dark craters themselves. What is actually down there, and what would it take to get it out? That will be a future ramble. If you want it when it comes, you know what to do. Meanwhile, big lake or question marks, tell us whose side you're on below.